So this work was part of my PhD at McGill, and it's about decomposing the drivers of polar amplification with a single column model. So I'm currently working in Exeter, and so my collaborators are Tim Merlis from McGill, who was my PhD advisor, Nick, and Brian Rose from Albany. Sure. Okay, so yeah, the motivation basically is to understand Arctic amplification, which is just that under increased CO2 you get more warming over the high latitudes, especially in the Arctic, compared to the rest of the planet. And so the drivers of this Arctic amplification are still debated. And one of the key papers that came out in 2014 was this paper by Pethan Morrison, and they decomposed the various drivers of tropical and Arctic warming. And the way to read this graph is to look at how each contributor contributes to tropical warming in the x-axis and Arctic warming in the y-axis. So for example, surface albedo doesn't contribute to any tropical warming, so it's on the zero axis here, but it does contribute to Arctic warming. And so then you can just look at each point's distance from the 1-to-1 line, and that tells you how each of these things contributes, how much they contribute to Arctic amplification. And one of the key drivers in this decomposition is the lapse rate feedback. And so the lapse rate feedback just refers to how the vertical structure of warming affects the required amount of surface temperature change to balance a given forcing. So if there's a larger temperature change in the upper troposphere, then you get a larger increase in outgoing long-wave radiation. So then you need a smaller increase in surface temperature to balance a given forcing. And inversely, if you get more warming near the surface, then you get less of an increase in OLR, so then you need more surface temperature change to balance a given forcing, so it's a destabilizing feedback. So just to make that very clear, I have here a latitudinal temperature change plot from Aquaplanet. Don't worry too much about what model it is, but it's clear that in the tropics you get top heavy warming, and in the high latitudes you get bottom heavy warming. And so you can match that to the lapse rate feedback, where in the high latitudes you have a positive or destabilizing lapse rate feedback, and in the tropics you have a stabilizing or negative lapse rate feedback. And so one of the key things about the lapse rate feedback in high latitudes, so we understand quite well what happens in the low latitudes in the tropics, because the vertical structure of temperature change, the vertical structure of temperature follows the moist adiabat. So given a certain temperature and surface humidity, you can sort of determine the whole vertical structure of temperature. So that's quite clear, but at high latitudes, we have a different story. The vertical structure of temperature change is forcing dependent. So this is from a paper by Cronin and Janssen in 2016. And in this paper, they derive the temperature structure of the polar troposphere given three main parameters. The first one is the long-wave optical depth, which is like the amount of CO2 in water vapor. One is the surface heat source, and the other is the atmospheric heat source. So if you vary the long-wave optical depth, or you can think of that as varying the CO2 or water vapor, you get a very bottom-heavy temperature change. However, if you vary the surface forcing, which you can think of as varying the solar constant or the ocean heat transport convergence, or the surface albedo, you get a bottom-heavy warming, but much less bottom-heavy than in the CO2 case. And if you vary the atmospheric heat transport convergence, you get, in this model, a vertically homogeneous temperature change, even though the model is very simple, so you wouldn't expect that in a natural GCM. Okay, so just to wrap up this introduction, the lapse rate feedback in this Pethan Morrison decomposition the largest contributor to Arctic amplification, and it refers to the vertical structure of temperature change. So we know that the high latitude lapse rate feedback contains contributions from different terms, because the vertical structure of temperature change in high latitudes depends on the various forcings. So our objective is to use a single column model to get a decomposition of the tropical and Arctic warming that doesn't depend on this lapse rate feedback term. So then we can understand what contributes to this term. So I want to explain in more detail how you get this decomposition. So I'm going to start from the very basics. So the sun receives a certain amount of solar radiation, some of which is absorbed, and then emits some long-wave radiation. There's a balance between absorbed solar radiation and outgoing long-wave radiation. Now, if you add CO2, you reduce the outgoing long-wave radiation, so that's a forcing F that you apply at the top of the atmosphere. Then the surface temperature is going to respond by increasing, and the top of atmosphere energy budget change is the temperature feedback delta T times the surface temperature change. But the surface temperature change is going to change other components of the climate, like the water vapor, the surface albedo, and the clouds. And those will then change the absorbed solar radiation or the outgoing long-wave radiation. And so the resulting change in the top of atmosphere energy budget is just the sum of these various feedbacks times the surface temperature change. And so between two equilibrium climates, you should have that the forcing plus the sum of all the feedbacks times the surface temperature change is equal to 0. And then you can decompose the temperature feedback into the Planck feedback, which refers to the vertically uniform temperature change, and then the lapse rate feedback, which is a deviation from vertically uniform temperature change. And then you can express it all as a function of latitude. Then you'd have to add a term for the change in convergence of atmospheric energy transport. And finally, you can also decompose this Planck feedback into the latitudinal mean of the Planck feedback and deviation from the latitudinal mean. And then you just put the term that is the latitudinal mean of the Planck feedback times the surface temperature change on one side, and divide everything by this latitudinal mean of the Planck feedback. And so then you get a surface temperature change decomposition according to various terms of the top of atmosphere energy budget that I show here. So the Planck, lapse rate, water vapor, atmospheric heat transport, surface heat source, which I add as an extra term, and then the forcing from CO2. So the important part is that in this decomposition, the amount of surface temperature change that is attributed to each term of the top of atmosphere energy budget, it gives you the amount of surface temperature change that is required to balance this top of atmosphere energy budget, assuming that the surface and atmospheric surface and atmospheric temperature change are vertically uniform. And so any deviation from vertically uniform temperature change is encapsulated in this lapse rate feedback term. And so obviously, since the lapse rate feedback is negative in the tropics and positive in the high latitudes, this then gives you the lapse rate feedback as a huge contributor to polar amplification. So I should add, I did this decomposition using an idealized GCM that I will talk about later on. And so then you can use this temperature change attribution and sort of, average out from in the tropics to plot your points on the x-axis, then average out on the high latitudes to plot your points on the y-axis. And then you get a similar decomposition to what I showed in the introduction from P-Fan Morrison. And so our objective will be to use a single column model to get an alternative plot to this, that will be a bit clearer because we won't have this lapse rate feedback time. Okay, yeah, so I just said that. So yeah, just get a similar decomposition to this, but without this lapse rate feedback time. So to do this, we use an idealized climate model. It's a very simple climate model that has no continents, no sea ice, no clouds, and no seasonality. And we force it with a quadrupling of CO2. Since it has no sea ice or clouds, and the real climate does, and that would lead to local positive feedbacks in the high latitudes. So we add surface heat sources on top of the quadrupling of CO2, only in the high latitudes, to have these two other temperature change curves. And in this plot, I just compare it to what happens in various CMIP6 models. And then we use a single column model. So a single column model is just a way of isolating the tropics and the high latitudes. And it's a radiative convective equilibrium model to which I add advection. And the objective of the single column model is to emulate the idealized GCM the best I can. So I impose the idealized GCM values for CO2. I take the water vapor profile from the idealized GCM, and the temperature tendencies from atmospheric energy transport are imposed on the single column model to represent the effect of atmospheric energy transport. So then the single column model does a relatively good job in emulating the behavior of the idealized GCM. So here I'm comparing the climatological temperature of the column model in red and idealized GCM in black. So it does well in the tropics, it does less well in the high latitudes, especially the inversion. We think it's due to the fact that in the single column model there's no boundary layer scheme. But the temperature change looks okay, so we think it doesn't matter that much. So the single column model, I forgot to say, is using ClimLab, which is a great resource, especially if you're learning stuff. It's really good, so you should use it. Sure. Okay. Yeah. So then you can take the single column model and then perturb everything in it. So I increase CO2, take the water vapor profile from the perturbed GCM simulation, add a surface heat source, and take the perturbed energy transport. And so here I'm comparing the temperature change from the GCM in the dashed lines and the temperature change from the single column model when everything is perturbed in the solid line. So again, it does really quite well in the tropics, less well in the poles, but the surface temperature change is good. And then, so you can then, the cool thing about this single column model is that you can individually perturb each element. So this brown line is what happens when I just perturb CO2. So you get approximately 2 degrees of warming at the surface in the tropics and about 3 degrees in the poles. And you see that the vertical structure of temperature change is the same basically in the tropics because of the presence of convection, which pins the temperature structure to the moist adiabat. However, in the high latitudes, you don't get that. And so in the high latitudes, the warming from just increasing CO2 is bottom heavy, which is consistent with the Cronin and Nansen results. And interestingly, even though the top of atmosphere forcing from CO2 is stronger in the tropics than the high latitudes, you end up with a smaller surface temperature change in the tropics relative to the high latitudes, just because of the presence of convection, which brings the warming maximum to the upper atmosphere and reduces the amount of surface temperature change in the tropics. Okay, and then you can do the same thing with water vapor, basically the same story. Bottom heavy warming from in the high latitudes because it's also an increase in long wave optical depth, and top heavy warming in the tropics. And again, you get more warming in the high latitudes in the tropics, even though the water vapor feedback from the top of atmosphere perspective is stronger in the tropics than the high latitudes. And then energy transport, which the change in energy transport cools the tropics and warms the high latitudes. However, it warms mostly the mid-troposphere in the high latitudes and not the surface that much. And then just a surface heat source, which warms the whole atmosphere, but in a bottom-heavy way. So then, yeah, we can use a single column model to compare the top of atmosphere Pfand-Mouritzen style attribution to the single column model attribution. So in the crosses is the top of atmosphere attribution. You can see that because there is the Planck and Lapse feedback. However, in the dots, it's the single column model attribution. And the way to understand, so yeah, obviously in the single column model, you don't have the Planck and Lapse feedback. And to understand the differences between the top of atmosphere method and the single column model method, if the warming is top heavy in the single column model, then you would have a smaller absolute value of surface temperature change attributed in the single column model. If it's bottom heavy in the single column model, then the single column model will attribute more surface temperature change in magnitude compared to the top of atmosphere method. And basically that's just because the top of atmosphere method, as I tried to explain in the introduction, kind of assumes that all of these top of atmosphere budget changes are compensated by vertically uniform temperature change. So if the warming is top heavy, then you get less surface temperature change in the single column model. And inversely, if it's bottom heavy, you get more surface temperature change in the column model. So in the tropics, everything is top heavy, so all of the magnitudes of the surface temperature changes are reduced. And so everything is closer to the y-axis. And in the high latitudes, everything is bottom heavy except the energy transport. So everything is pushed away from the x-axis except the energy transport, which is brought closer to the x-axis. So you can do the same decomposition without the surface heat source. And the bottom line here is that adding a surface heat source reduces the contribution of the energy transport, which is consistent with previous work. So in summary, let's see how much time I've used. 20 minutes, roughly. In summary, the single column model is used to modify this surface temperature change attribution method to account for the forcing dependence of the lapse rate feedback at high latitudes. So then if we want to zoom out and think about what do we learn from this different decomposition, one thing we learn is that even though both CO2 forcing and water vapor feedback are stronger in the top of atmosphere sense in the tropics than the high latitudes, they actually contribute to polar amplification because of the presence of convection in the tropics, which brings the warming maximum to the upper atmosphere and cools the surface. And atmospheric energy transport convergence preferentially warms the mid-troposphere, and adding a polar surface heat source reduces the contribution of atmospheric energy transport.